Hello everyone, my name is Maxim Dosta. I'm an assistant professor for multi-scale simulation of solid processes at Hamburg University of Technology, and in this short introductional video I want to explain how you can use Dyssol system in order to perform simulation of granulation process. The aim of this task is to perform simulation of following urea granulation process. This process, it is continuous granulation process consisting of fluidized pads, screens and a mill. How it works? So we have external nuclear stream which comes to apparatus. The solution is injected. The granulation takes place and the formed granules come to the first screen. The oversize of the first screen is milled and mixed with undersize of a second screen. Afterwards, the stream is recycled back to a system. And as a product, we take only particles which are smaller than specific cut diameter of the first one and which are larger than specific cut diameter of the second screen. Moreover, there exists one additional gas flow in order to perform fluidization. And we have also one additional outlet flow for dust. Now, in order to reproduce this scheme in a Dyssol, it is necessary to create a coding number of unit operation and a coding number of streams. Let's firstly just count how many unit operations are involved in this process. We have 1, 2, 3 inlet streams, 2 outlet streams, we have 1, 2, 3, 4 apparatuses, and as well as 2 additional mixers. So overall we have 5 plus 4 plus 2, 11 different unit operations. Now we can count material streams. This will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Overall we need 12 material streams. Now let's recreate the structure in the Dyssol. Now I've opened an empty instance of a Dyssol and I can add a coding number of unit operation and a coding number of material streams. It says that we need 11 unit operation and 12 material streams. According to the given process structure, I will rename my unit operation. So this will be urea solution, this will be nuclei, that will be fluidization gas. Next one will be granulator, no, mixer 1, and we can continue to rename all unit operations as well as all material streams. So now I have defined all my unit operations and material streams. In the next step, I can save the flowsheet as separate file. So, okay, in the next step, it is necessary to define for each specific unit operation a coding model. For example, for inlet flow of urea solution, we will use inlet flow. The same one will be for nuclei as well as for fluidization gas. So these are our 3 input streams. For mixer, I will pick mixer, granulator, this will be granulator, screen 1 as well as screen 2 will be modeled using the models of a screen, mill, this will be a model of a crusher, and for outlet flows I will also pick according outlet flows. In the next step, it is necessary to define connections between unit operations and material streams. So this means it's necessary to define, for example, for first unit operation, what will be the outlet stream which comes from this unit operation. In this case, it will be in solution. For nuclei, it will be in nuclei. Fluidization gas, it will be in gas. For a mixer, here, according to the process structure, for a mixer we have 2 inlet streams. This will be in nuclei as well as mix out nuclei. And as output of the mixer 1 we have stream which is named mix in nuclei. Now In similar manner, I can define all connections between the unit operations and material streams. Now we have defined all connections between the unit operations and material stream. And in the next step, what we can do, we can define all other necessary settings. First of all, it is necessary to define the compounds which will be used to perform the simulation. For the modeling of urea granulation, we need air, we need water, as well as we need urea. So 3 different compounds. Next stage is necessary to define the phases which will be involved in this process. We'll have here 3 different phases. This will be solid phase, liquid phase, and gas phase. And according to that, I should pick correct state of aggregation. It will be solid, liquid, and vapor. Next important step, it is definition of distribution grids. As compound, as upper layer of dimensions which we have, it is always compounds. And a second dimension, a second property coordinate, I will pick the size. And to perform simulation of urea granulation, I will use equidistant grid with 100 size classes, and the dimensions of it will be from 0 up to 4 millimeters. In the next step, it is necessary to define holdups. Just a short reminder, all input streams are defined as streams which have specific holdup, infinitely large holdup. That's why if we want to define what exactly comes into a system, then we should define the holdup of according fit. Like, for example, first of all, we'll define urea solution which comes into a system. What we will do, we add one time point 0, and it's necessary to define the mass flow. The mass flow for this stream will be 0.35 kilogram per second. Next stage, it's necessary to define phase fraction. This urea solution, it consists from 80% of solid and 20% of a liquid. Now for liquid phase, we define which compounds they exist. This will be water, for gas phase air, and for solid phase it will be urea. Theoretically, it doesn't matter what we define here for gas phase, because there is no gas flow, but in order to avoid any problems during the calculation, I will just put that the gas phase consists only of the air. Now, theoretically, for urea, it is necessary for any solid stream to define its distribution according to a size. But here, we are talking about solutions. This means that this urea doesn't have any size distribution. That's why it doesn't matter what you will define here. So this means that some sort of default values can be used. Now, next step, we define nuclei. The same procedure. So we add one additional time point, we define the mass flow. In this case, this will be 0.05 kilogram per second. Phase fraction, it will consist only on a solid phase. For liquid gas phase, I will use the same, and for solid phase, it totally consists from urea. But now here, for nuclei, it's necessary to define correct particle size distribution. In this case, I will use normal distribution with median size of 1 millimeter and standard deviation of 0.15 millimeter. Next stage, it's fluidization gas. Here, I will also add one additional time point. I will define mass flow, it will be 2 kilogram per second. Phase fraction, it is consist only on the gas phase. And I can also define distribution of compounds in this phase. Next important stage, it's granulator. it's necessary to define the holdup in the granulator in the initial time point. First of all, here we will define the mass of it, 100 kilogram. Phase fraction, it will consist only on a solid phase. So the solid phase will consist only on urea, and it's necessary to define initial particle size distribution. As in the case of nuclei, here the initial diameter will be 1 millimeter, but the standard deviation will be slightly modified. It will be 0.1 millimeter. Now we have defined all holdups, which is necessary to define in this. Next stage, what is necessary to do is necessary to define parameters for unit operations. Some of unit operations, like inlet flows, they don't have any parameters, but granulator or screen and the mill, they have specific parameters which should be defined. First of all, for granulator, we define overspray rate. We will use default value equal to 0, and it's necessary to define relative and absolute tolerances. The both tolerances are used in internal solver to solve differential algebraic equations, and in this case I will just decrease tolerance into 1e-5 and 1e-6. Screen, to define the material of a screen, I will use the model according to a plate with cut particle diameter of 14 mm, separation sharpness of 8, and for second one I will use 1 mm and same separation sharpness. The next model, it's a meaning. Here the constant model will be used. This means that the output particle size distribution is directly described. In this case we have mean diameter of 0.9 mm and standard deviation of 0.1 mm. And the last important part which should be defined here is to define calculation options. Here we should specify relative and absolute tolerances for calculations. I will specify them as 1e-4 and 1e-8. Later on, it's necessary to define the convergence method. So in this case, the default value will be used, the Weckstein method and extrapolation method. I will just pick linear extrapolation methods. Definitely the options which you specify for calculations, they strongly depends on the type of process which you solve. For example, these options well suited to perform simulation for given parameter set. And now I can perform a simulation, and I will specify 36,000 of seconds as end time point. And if everything was defined correctly, I can perform simulation. So you can see, for example, now the time which is reached. So currently we reach already 12,000 seconds, and already now we have the simulation has been finished. Now I can jump to my simulation results and see what's happened within the process. I want to see the solid distribution in the graphical representation. And with the time slider we can see how the particle size distribution is modified. So we start with median size of 1 millimeter, and with the time we have enlargement of particles as well as some sort of dynamic process caused due to the existence of screens and due to the existence of recirculation streams. So we can, for example, compare granules and input nuclei streams in the initial time points and later on how it is changed. It is also of great interest to see the mass flows in the system, not only particle size distribution. For example, this recirculation mass stream which we have in the system, that, for example, outlet flow. Just please keep in mind, sometimes you can see some sort of such deviations, like this is some sort of numerical error, which you can just easily assume that it is constant, because if you will look now to the deviations, these deviations are neglectably small. and they cause due to the sequential modular way how the scheme is calculated. For example, the mass flow of affines within the process. So we see that something like after maybe 15,000 seconds, we have steady state. Now what we can do, we can analyze some sort of dynamic change of different parameters. That's why what we will do, we will go to the Holdups definition and see what will happen if we will have some sort of modification of nuclei mass flow. In order to do that, we will add 2 additional time points, like 10,000 seconds and maybe 11,000 seconds. And we will say that from 0 up to 10,000 seconds, our mass flow of external nuclei will be always 5 grams per second. But starting from 10,000 seconds, it will be increased up to 0.009 to 9 grams per second. Now we can perform simulations once more and see how large this influence. Now let's look to simulation results. So as expected, if we look now onto the process outlet flow of the product, until 10,000 seconds it is a constant, and from 10 up to 11,000 seconds we have linear increase of it, and later on we have also one constant flow. We can also analyze how the recirculating stream are modified in the system. We have some sort of dynamic process, and starting from 10,000 seconds we increase linearly and the external nucleus flow. That's why we have here this steep change. But also we can, for example, analyze the outer distribution, the outer diameter of, for example, of our product, how it changed. So we have some sort of oscillations, and which influenced by the modification of the external nucleus stream. And let's look now to the dynamic change of particle size distribution in the system. We have here some sort of oscillations, and we will reach steady state. So this is exactly how you can perform simulation of the granulation in a Dyssol system. Thank you.